So, welcome to my dear friends and learners. So, today we'll be discussing about the compounding. Already in the previous lecture, we have discussed why instead of single stage energy extraction, why it is advisable to extract the energy from the high pressure steam in several stages. And this methodology is called compounding. So, in nutshell, you can tell that compounding is a method of extracting the energy from steam in multiple stages to enhance the efficiency of the turbine by reducing the rotor turbine speed. Okay, basically it's an strategic, or it's a uh, predefined arrangement of uh, multiple sets of fixed and moving blades within the single casing of the turbine uh, to uh, extract the energy from high pressure steam, which will definitely uh, address the issue of the rotor high speed, means the speed with lesser angular speed. We will be able to extract the energy. This will definitely improve the vibration performance, and also the structural design, as well as the uh, mm, material selection. It will be much more easier. So now you can see this arrangement here. There are multiple, this, you see, first there is a nozzle, then one moving blade, then one nozzle, another moving blade, then another nozzle and moving blade, like that. Okay, this arrangement is called the pressure compounding, and you can see here, this position, this is your steam pressure, and finally this is the condenser pressure or the exhaust pressure. Now you can see this pressure drop is taking place in several stages. Okay, so this is your stage 1, this is your stage 2, uh, and this is your stage 3. Okay, you should, to analyze this concept, here two things to be remembered. If the aperture, through which the fluid is moving, or fluid is flowing, if there is no if the aperture is uniform, that means there is no differential pressure, then means if the aperture is uniform, so there will be no differential pressure. Okay, and if there is a change of aperture, definitely there will be a pressure drop, and once there is a pressure drop, the velocity will increase. Okay, so this is explained in a momentum equation. And also the momentum will change if there is a change of momentum, or if the kinetic energy change, there is a change of momentum. In this way, the energy transfer will also take place. So now you see, if in the nozzle through which here the steam is through this, the high pressure steam is entering, and here's you see there is a change of aperture, and then it is expanding. So definitely there is a differential across this orifice, or across this cross section. There will be a change of differential pressure. There is a dp, so that's why you see the pressure is getting reduced. And once there is a differential pressure, so definitely your velocity will increase, and you see the velocity is increasing. And then while it is entering in the moving blade, and you see the cross section, this cross section, those are uniform. So once the fluid is flowing through a uniform cross sectional aperture, so there is no pressure drop, as I told. So you see the pressure is constant, but impulse due to the impulsive effect or the reaction, the turbine blade start to rotate, and here the uh, uh, energy transfer will take place. So definitely the kinetic energy by means of velocity of the steam, the energy is getting transferred to the rotor in the moving blade, and the turbine start to rotate. So there is a transfer of kinetic energy, hence the momentum. And due to this reason, the um, uh, steam will lose some energy, and due to that the velocity is getting dropped. And after that, while the steam is again entering inside the nozzle, so again there is a differential pressure due to this orifice. Okay, and again due to, as there is a differential pressure, so this is due to that there is a pressure drop, and once there is a pressure drop, so again the velocity is getting increased, and that higher velocity steam is entering inside the next stage of moving blade, and there the aperture is uniform, so further there is no change of pressure, but here the by the by the movement of the rotor blade, the kinetic energy is getting transferred, so again steam is losing its kinetic energy, so the velocity is dropped, and same thing is repeating in the next stage. So this arrangement here we can if you see in case of impulse turbine, so if there is a single sets of blade, so what will happen, so there is that huge as the pressure is the steam pressure will be uh, very high. Normally it will be around 150 or 200 kg also. So that high pressure steam, once it is getting expanded through the blade and coming to the condenser pressure, So there is a huge pressure drop. This is due to that huge pressure drop, it is causing higher rotational speed of the turbine. This is addressed here, and this technique is called, this arrangement is called pressure compounding. Now coming to the next arrangement. Here you see uh, there is a single nozzle, but this is the moving blade, and this is the fixed blade. This also work indirectly as a nozzle. These blades are connected with the turbine casing, and then again the moving blade. So what will happen here, as there is a orifice, so the differential pressure. So once the pressure is dropped, the velocity is increasing, and once the velocity, that high pressure steam entering in the passage of the moving blade, so the energy transfer is taking place. It's an adiabatic process, and due to that the steam is losing its kinetic energy. So that's why the velocity of the steam is getting reduced. But as the fixed blade cross section is uniform, so due to that there is no pressure change. There is no change of here there is no change of pressure. And you see here, the entire in the passage of the moving blades and also in the fixed blade, those cross sections are uniform. So during the entire energy extraction process, there is no change of the pressure. Okay, and directly it is reaching the uh, exhaust uh, pressure. Okay, and as in the fixed blade there is no energy transfer, so that's why velocity is maintained. And after that, once it is again entering the moving blade passage, so there is again kinetic energy transfer, and the velocity is getting reduced. So this arrangement is called velocity compounding. Okay, now coming to the third arrangement. If you see here, whatever the pressure compounding and the velocity compounding we learned, that is combined together. Okay, so this basically, this arrangement is called your once it is repeating, this is your pressure compounding. Okay, you see, this is one set of nozzle, this, and one set of if you remember this arrangement. Okay, so there is a sets of nozzle and moving blades are cascaded together. So these things is happening here. So this is pressure compounding, and in this arrangement there is a moving blade, fixed blade, and again moving blade. So this is for velocity compounding. So once this arrangement is made together, so this will give you the pressure and the velocity compounding together, which is called pressure velocity compounding. Okay, similarly you can explain this curve here also, because the nozzle having this nozzle causing the differential pressure, so there is a pressure drop, and once there is a pressure drop, so the velocity is getting increased, and after that this e- either the moving blade or the fixed blade, those cross sections are uniform. So in that entire stage A, there will be no pressure drop, but in the moving blade, the energy transfer is taking place. The kinetic energy is getting transferred. So the kinetic energy of the steam is getting transferred to the moving blade. So that's why there is a velocity drop. And in the fixed blade, it is no energy is getting transferred, so there is that's why the velocity is constant. And again, in the second row of moving blade, there is a kinetic energy transfer from steam to moving blade, that's why the velocity is getting dropped. And after first stage of energy extraction, while again it is entering into the second sets of nozzles, due due to the orifice, again the velocity is getting increased because the pressure is getting dropped, and these things are getting repeated. So this arrangement is called pressure velocity compounding. And here basically this is the practical arrangement. We will discuss these things later on in with more mathematical analysis. So here, this the sets of, so this is the first stage, this is the second stage, this is the third stage, like that. Okay, here if you see the cross section, the cross section of the fixed blade which act as nozzle, that is also not uniform, and the passage between the moving blade, th- this also not uniform. So due to this non-uniform cross section in the fixed blade arrangement, this also work as a orifice, and there is a pressure drop, and due to that the steam velocity is getting increased. And while it is the high pressure, the high velocity steam, while it is entering in the passage of the moving blade, there will be a pressure drop, as well as due to this non-uniform passage between the moving blade, it will also work as a nozzle or uh, as an orifice, so there will be a pressure drop. And also, the as this is a sets of moving blade, so the energy will, the kinetic energy also will getting transferred from steam to the uh, moving blade. So that's why there is a velocity drop in the steam. And again, due to this, after extracting the energy from the first stage, once the steam is entering in the second sets of fixed blade, and due to the non-uniform aperture, there is a pressure drop, and again the velocity is getting increased, and so on. So basically this is the practical steam turbine, which is Sendil, I am in a class. I will call you back within 10-15 minutes. Oh, so basically this is the uh, practical steam turbine of our interest, and we will elaborate these things in detailed way during the subsequent lectures. So hope the compounding of steam turbine you have understood. I will not extend today's discussion furthermore because I have some work. So hope it will be useful and you have learned something. Thank you so much. Thanks for your patience.